Welcome to problem set 28. Our problems today will be from the topic carbohydrate metabolism and glycolysis. Before we get started, just a quick reminder that the worksheet to accompany this video is available online through my website. And with that said, let's get started with number one. Number one, what monosaccharides result from the hydrolysis of lactose by the lactase enzyme? So this problem really goes back to when we first started talking about carbohydrates. That was quite a few tutorials ago. But hopefully you remember the two monosaccharides that make up the disaccharide lactose. They are glucose and galactose. So when the glycosidic bond that links those two monosaccharides together is hydrolyzed in digestion, lactose will free up the monosaccharides glucose and galactose. All right, number two. What is the final product from the 10-step process of glycolysis? Remember that glycolysis is the process in which the 6-carbon molecule glucose is broken down into 2 molecules of pyruvate. So the final product is 2 molecules of pyruvate. Okay, number 3. Consider your answer from number 2. How many carbon atoms are in one molecule of this product? So remember, in glycolysis, the 6-carbon molecule of glucose is broken down into 2 3-carbon molecules of pyruvate. So there are 3 carbons in a pyruvate molecule. Number 4. Consider your answer from number 2 again. What is the fate of this molecule under aerobic conditions? Okay, so when oxygen is plentiful under aerobic conditions, pyruvate will be oxidized into acetyl coenzyme A and carbon dioxide. So let's write oxidation into acetyl coenzyme A and carbon dioxide. So remember that the food molecules turn into the 2-carbon portion, the acetyl portion of acetyl coenzyme A. So that 3rd carbon from pyruvate got oxidized all the way to CO2. All right, number 5. Refer to slide 3 of tutorial 28 or any other source that shows the steps of glycolysis and answer A through B below. So I happen to have slide 3 right here. I'm going to hang it up on the board so I can refer to it. You probably can't see that, but hopefully you have the notes from tutorial 28 as well, or if you don't, just look up glycolysis in your textbook or online. All right, part A. Which step, or which steps plural, involve the reduction of a coenzyme? Okay, so we're just looking at these steps, looking for the steps that involve the reduction of a coenzyme, which means a substrate is getting oxidized. So that's only happening on step 6. We can see the oxidized coenzyme NAD+ is reduced to NADH, H+. So only step 6 involves the reduction of a coenzyme. Okay, part B. Which step, or which steps plural, result in the direct synthesis of ATP? Now, when we look at this, we see ATP involved quite a bit, but make sure that you notice that step 1, although ATP is involved on step 1, that ATP is actually being used as a source of phosphate. So it's being converted into ADP. It is not being synthesized. So don't write step 1. Same thing on step 3. ATP is being used as a source of phosphate. So being converted into ADP. So it's not being synthesized. It's being used. All right, go over to the second half. And we see on step 7 that ADP is converted into ATP. So ATP is synthesized on step 7, and that's happening as well on step 10. ADP is being phosphorylated and converted into ATP. So ATP is synthesized in step 7 and step 10. So it's right here, steps number 7 and number 10. Okay. Number 6, put the following in order of occurrence: Krebs cycle, glycolysis, oxidative phosphorylation, pyruvate oxidation, and the electron transport chain. So in other words, what is happening first, second, third, etc. So first, out of all of these different processes, the first is glycolysis. Glycolysis happens first. That's a process in which glucose is broken down into 2,3 carbon molecules of pyruvate. After glycolysis, remember that that pyruvate has to be oxidized. So number 2 would be pyruvate oxidation. And in pyruvate oxidation, the pyruvate is converted into the acetyl portion of acetyl coenzyme A and a carbon dioxide. Acetyl coenzyme A, in complete catabolism, is going to enter into the Krebs cycle. So number 3 is the Krebs cycle. The electron transport chain follows the Krebs cycle, and in the electron transport chain, all those reduced coenzymes from the previous processes will get reoxidized and then can be reused. So the electron transport chain, I'll write ETC. The electron transport chain is next to reoxidize all those reduced coenzymes. And then remember that the energy harnessed from the electron transport chain is used to power oxidative phosphorylation. That is the phosphorylation of ADP into ATP. So we should write oxidative phosphorylation. Last. Okay. Number 7. I think we're going to need a little more room here, so let's go ahead and erase before we go on to number 7. Okay, number 7. Calculate the number of moles of ATP that forms from complete catabolism of 1 mole of glucose. Show the ATP yield from each of the following processes during their calculation: Krebs cycle, glycolysis, oxidative phosphorylation, pyruvate oxidation, and the electron transport chain. All right, so 1 mole of glucose. The question is, how many moles of ATP are you going to get from the complete catabolism of 1 mole of glucose? So it's good to kind of think through the whole process of glucose catabolism. We know that glucose is first going to be broken down into 2 molecules of pyruvate, and that happens in the 10-step process known as glycolysis. Each pyruvate is then going to be oxidized into 2 molecules of acetyl coenzyme A. And carbon dioxide is lost in that process. That is a process known as pyruvate oxidation. Okay. And it's the acetyl coenzyme A that can enter into the Krebs cycle. where the acetyl portion is going to be fully oxidized into carbon dioxide. We're going to get some GTP, and from that oxidation we get reduced coenzymes 3-NADH, H+, and 1-FAD-H2. Those are going to be reoxidized in the electron transport chain, which is going to provide the energy needed for oxidative phosphorylation. So I'm going to write OX for oxidative phosphorylation. Again, we know that ultimately the electrons and the hydrogen ions are passed to oxygen from the air that we breathe to make water. This highly exergonic process is used to provide the energy to synthesize ATP from ADP. Phosphorylate ADP, making ATP. The result is that those coenzymes are reoxidized. And they can go back and be reused to power these processes again. All right, so how much ATP, we'll do it in green, do we get from each of these processes? So we have to account for the ATP that's going to come from glycolysis, pyruvate oxidation, and the Krebs cycle. And I like to just go ahead and account for the electron transport chain and oxidative phosphorylation as I go. So as I see reduced coenzymes, I'll go ahead and do the ATP yield for electron transport chain and oxidative phosphorylation as we go. All right, so in glycolysis, if you need to, go back and look at slide 3 from the notes, and you can see where ATP is being synthesized and reduced coenzymes are being synthesized. So overall, we know that it's -2 ATP to get the process going, to start. Remember, we have to phosphorylate that glucose molecule twice, making that sort of symmetrical looking molecule that's going to be cleaved in half on step 4 to make the 2 3-carbon phosphorylated 3-carbon molecules that will then carry on and be converted into the 2 molecules of pyruvate. So it takes 2 ATP to do that. Then we're going to get 4 ATP in the end, in the second half of glycolysis. Remember that we get 2 ATP for each D-glyceraldehyde 3-phosphate undergoing steps 6 through 10. So I'm going to write that little note right here. Remember that it's +2 ATP per G3P molecule undergoing steps 6 through 10. We get 2 of them, so it happens twice. Okay. And we get 2 reduced coenzymes of NADH in that second half of glycolysis. Again, if you go back and look at the process, you're going to be saying, I only see 1. Where's the other one? Remember that steps 6 through 10 happen twice because 1 glucose makes 2 3-carbon molecules of D-glyceraldehyde 3-phosphate, and each of those undergoes steps 6 through 10 separately to make pyruvate. Okay, so I'm going to write here +1 NADH H+ per G3P, per D-glyceraldehyde 3-phosphate. Okay, remember that's how I abbreviate D-glyceraldehyde 3-phosphate so that I don't have to write it out over and over and over. All right, so in the electron transport chain, later on in the electron transport chain and oxidative phosphorylation, when the 2 NADH are reoxidized, we're going to get ×3 ATP. Remember that each NADH is going to make 3 ATP. So 2 × 3, we're going to get 6 ATP later on when the reduced coenzymes are reoxidized, and their reoxidation will power the oxidative phosphorylation. That is the phosphorylation of ADP into ATP. So total here, where are we at? We've got 6 plus 4, that's 10, but don't forget to minus the 2. So we've got 8 ATP from glycolysis. Okay, so I'm going to check this off. We did that one. Going to keep track of where we are. It's a lot of work. All right, now from that process, we ended up with 2 molecules of pyruvate. Each of those molecules is going to be oxidized in complete catabolism into acetyl coenzyme A and carbon dioxide. So in order for that oxidation to happen, a coenzyme needs to get reduced. We get plus 1 NADH, H plus, but remember it happens twice, so times that by 2. We get plus 2 NADH, H plus. Later on, those will be reoxidized in the electron transport chain, ultimately passing their electrons and hydrogen ions to oxygen from the air that we breathe, making H2O, and that highly exergonic process is going to be utilized to power the synthesis of ATP from ADP. So times that by 3, because for every 1 NADH that's reoxidized, we make theoretical yield 3 ATP. So 2 times 3, we get 6 ATP. All right, plus. And I'm going to circle these to make them easier to find when we go to add them all up at the end. All right, now we've got acetyl coenzyme A. That's ready for the Krebs cycle. But we get 2 of them. So we get 2 full turns in the Krebs cycle, not just 1. So remember, and you can go back and look at the Krebs cycle if you need to, that from 1 turn in the Krebs cycle, you get 3 reduced coenzymes of NADH, H plus, it's really just what we wrote down here, and 1 reduced coenzyme of FAD, H2, plus we get the high energy molecule GTP. For each turn in the Krebs cycle, we make 1 GTP, which we're just going to consider as an ATP. Adenosine triphosphate and guanosine triphosphate, both high energy molecules. Later on, in the electron transport chain and oxidative phosphorylation, these reduced coenzymes will be reoxidized, providing the energy to power oxidative phosphorylation, or the phosphorylation of ADP into ATP. So times that by 3, you get 9 ATP from the reoxidation of the 3 NADHs, and times this one by 2. Don't forget, it enters the electron transport chain at a later point, thereby producing less energy, which means less energy available to synthesize ATP. So you get a lower yield of ATP. Okay, so times 2, not 3. So 2 ATP from the reoxidation of the FADH2. Total, plus 9, 10, 11, 12 ATP per turn in the Krebs cycle, but we get 2 turns because we've got 2 acetyl coenzyme A's from the glucose breaking down. Okay, so times that by 2, you've got 24, I'm going to put plus 24 ATP. And again, I already accounted for the electron transport chain and oxidative phosphorylation as we went along. I think it's easier to do it that way. Okay, instead of saving it and doing it at the end, it makes sense to just do it as we go along. So we talked about pyruvate oxidation, and we talked about the Krebs cycle, and we did the electron transport chain and oxidative phosphorylation as we went along. So now we're ready to add them up and see what our net yield of ATP will be from that 1 mole of glucose being completely catabolized. Okay, so we've got 24 and 6 and 8. So that's 38 moles of ATP. Watch your units here. Because I said 1 mole of glucose, we want to give our answer in moles of ATP. 1 molecule of glucose would give us 38 molecules of ATP. 1 mole of glucose, which is 6.022 times 10 to the 23rd molecules, would give us the 38 moles of ATP. Okay, so 38 times the 6.022 times 10 to the 23rd molecules of ATP. So watch your units. Just because I was asking for 1 mole of glucose, make sure you put your answer in moles of ATP. Last but not least, and then we will be done with this problem set. If your instructor or your textbook uses the actual yields from the electron transport chain and oxidative phosphorylation, then they will be multiplying by 2.5 and 1.5 instead of 3 and 2. That will make your answer come out to 32 moles of ATP. So make sure that you understand if your instructor or your textbook is utilizing those actual ATP yields from the electron transport chain and oxidative phosphorylation. I myself, and the textbooks that I always use when I teach biochemistry, always use the max yield, which is 3 ATP for every 1 NADH reoxidized and 2 ATP for every 1 FADH2 reoxidized. All right. Thank you very much for tuning in to problem set 28. I hope you will consider tuning in to tutorial 29.